Hello everyone, my name is Jumin Lee, one of the TAs, and I am a PhD student in SGBR lab, which is led by the Professor Hyun. So today we are going to talk about the introduction of diffusion models, one of the famous things in the generative model. Diffusion model began just 4 years ago with the publication of the denoising diffusion probabilistic models. This research demonstrates the quality of the generating highly realistic image. And then just 2 years later, the researcher developed rapidly with the text conditions. So one of the most well-known paper is the stable diffusion. Unlike a previous DALI or ImageGen, stable diffusion was released as the open source. And by doing so, it has the impact on development in the field. So as conditional generations gain attention, many applications emerge. One of them is in painting. It regenerates the selected area of the image. These applications focus on the seamless blending the regenerated area with the original image. Contrary to in painting, outpainting is generate the new contents outside the boundary of the existing image. So similar to in painting, the challenges here lies in the smoothly blending the new contents with the existing image. Compared to the in painting and outpainting, image-to-image generations aim to incorporate more of the user's intentions by providing the stronger conditioning input. So it used the bounding box or segmentation mappings as conditions to generate a new image. As mentioned earlier, text-to-image generation is another method to reflect the user's intentions. Many models are being developed to improve the quality of the generated image based on the descriptions. Moving beyond 2D image, diffusion model has also been explored to generating 3D object. Initially, they generate the object composed of the point clouds representing the location in the space. And now it has developed to generate object with the RGB value, adding color and detail to the 3D structure. And some of these models are capable of the text to 3D generations, which show the promising results. Recently, researchers tried to generate 4D objects incorporating both spatial and temporal dimensions. In this work, diffusion models generate images of objects from multiple viewpoints and at the different time steps. So these images are then used to train the other models to construct the 4D representations. While directly 4D generations by diffusion model is not yet, however, we expect this progress soon. To understand these applications, let me explain the basic theory about the diffusion models. The concept of diffusion is in thermodynamics. Imagine dropping a single drop of ink into the water. Over time, the ink molecule gradually disperses into the water. As shown on the right, the boundary between the ink and water particles slowly blend together. If we reverse this video and zoom in on the boundary, it becomes impossible to distinguish whether the particles are blending or separating. The reason for this lies in the nature of the ink movements over a very short time. These molecules move in small random steps that follow the Gaussian distributions. When we think about the well-blended ink and water back into their original state in small time steps, the movements of this molecule would be the same with the Gaussian distribution. So diffusion model apply this molecular movements concept to image pixel value. Diffusion model consists of the two processes, forward diffusion process that gradually add noise to the input. This process is shown on this figure from left to right. It starts from the image of cat and gonna add Gaussian noise to image each time step. The forward process does this in so many steps such that eventually on the right side, which is the white noise distribution. The second process is the reverse denoising process that runs to generate data noise. This process is shown on this slide from right to left. So this process will take a noise image and it will generate a less noise version of it, and it will be repeat this process such that it can convert noise to data. When we think about the training a diffusion model, the algorithm is as straightforward as the process we've discussed. So as seen on the line 5 of our algorithm, the output of UNet model is a Gaussian noise. The noise is what needs to be removed to generate the less noisy version, which is xt-1, from the input noise image, the xt. Thus, the loss function is essentially the difference between the Gaussian noise and the model's output. During training, the models learn from time step t within the range of the large T. So T is also provided as the input to the UNet. After training, during the sampling time, the noise is progressively removed at each time step up to the large T. So to better understand this process, let me explain the line 4 and line 5 in this algorithm. As mentioned earlier, fourth diffusion process in which we add small amount of Gaussian noise to the sample in the T step, producing a sequence of the noise sample x1 to xt. The corresponding equations can be seen in the first row. And by applying the Markov property, which states that the next step depends on only the current step, we can derive the second row equations. So this allowed us to directly calculate the image at time step t from the clean image x0 without going through all the intermediate steps. So as the result, we can sample an image xt from this Gaussian distribution as shown in the third line. Next, in the reverse process, we cannot easily estimate the first row equations because it needs to use the entire dataset, and therefore we need to learn a model to approximate this conditional probability in order to learn the reverse diffusion process. This enables the diffusion model to generate high quality and diverse things. However, diffusion models have significant drawbacks. As the image size increases, the resolution of the process is also increased. So this leads to the higher computational cost. To address this, the latent diffusion model has been developed, which operate in a smaller, more efficient latent space rather than the large pixel space. It is motivated by the observations that most semantic and conceptual meaning of the image is still remain after compressions. So in the latent diffusion model, the compression process rely on the autoencoder. Autoencoders are designed to learn efficient representation of data, typically for the purpose of the dimension reductions. So autoencoder consists of the two main parts. First one is the encoder. This part compresses the input image into the lower dimensional latent representations. And second part is a decoder. This part reconstructs the image from its latent representations. So in the latent diffusion model, the encoder compresses the image into the latent space where the diffusions and denoising process occur, and this is significantly reduce the computational cost. compared to the in pixel level diffusion. So the decoders then reconstruct the high quality image from the denoise latent representations. So it can efficiently generate image while preserving quality. So inspired by these latent diffusions, our goal is generating 3D semantic scene, not all object level generations. So what makes our task different from the image generation is that we are dealing with the 3D dataset. So our dataset is voxels, which you can think that as a 3D version of the pixels. So each voxels has the semantic label that represent the multiple objects. And so our goal is to create this data structure using diffusion models. So we propose two ways to address this task. In the first paper, we used diffusion model for the first time on the 3D semantic data and showed the significance results. And we also emphasized that creating multiple objects due to the nature of the semantic map is not covered by 3D object shape generations. And in the second paper, we enhance the generation performance and conduct on the real data as well as the synthetic data. And we also extend our model with the several applications such as in-painting and out-painting as in the image diffusion. So our first paper's name is the SSD, Diffusion Probabilistic Model for Scene-Scale 3D Categorical Data. So SSD followed the same strategy of the latent diffusions. In first stage, autoencoder learns to 3D semantic map into the latent representations by reconstructing scene. However, our dataset is the 3D, so we have to 3D latent representations unlike image latent diffusion models. So we have to utilize 3D unit structure in both stage 1 and stage 2, which is the training diffusion model stage. So we have seen pretty good results with SSD on synthetic dataset. However, SSD compressed the scene into 3D latent, which inevitably incurred the computational overhead. In addition, there are many empty regions like sky in the semantic map that actually not important things to model, but it must be represented by the voxels. So it makes model difficult to focus on a small object. In particular, we had trouble training on real dataset because real dataset has more higher resolutions and there is more empty space than synthetic data because it consists of the it can collect from the real sensors which have inherent limitations such as their limited field of view or inability to capture occluded regions. So also, we can see different sizes of object from small like a traffic sign to the large thing like a road or building. We present SAM-3 semantic scene generation with triplane diffusions to address this problem. As I mentioned, our previous method is using a voxel latent space figure in this figure in the left. However, in the second paper, we selected the right one, which is the triplane. This representation is vectorized the 3D data into the three orthogonal 2D planes. So it is not only more efficient than using a voxel latent, but it also provides more detailed information compared to the bird's-eye view representations. Additionally, it can include the explicitly spatial informations. It means that we know the 3D coordinate with these representations, compared with the implicit function. So our expectation of using triplane for generating scene is followed. Triplane can encode efficiently an expressive real categorical scene even if it has a high resolution and lots of empty area. and it has the spatial awareness that helps capture the semantic and geometric complexity between multiple objects within the scene. So this is the overall architecture, which has the two-stage training like a latent diffusion. Only different thing is the latent space is changed to the triplane. So first triplane representation is learned by our autoencoder. Then our diffusion model learned this triplane distribution to generate a novel triplane. Inference time, triplane generations lead to the 3D scene through decoding with the MLP, which train at the first stage. So this is the visualization of our generation process. As you can see the results, SAMST will generate diverse and realistic outdoor environments than SSD, which use the voxel representations. So it demonstrates that beyond data efficiency, the triplane excel in the focusing on objects such as the small thing like vehicle and building, by less attention on the redundant elements like air. So we evaluate scene generation performance in terms of the diversity and fidelity. Here, fidelity means that how well the model can learn and reproduce the characteristic of the training data. For example, the model with the high fidelity reflects the detail and patterns learned from the training data very well. So each metric is computed between the rendered image of generated scene and dataset. So SAMCT shows significant improvement compared with the previous SSD in both fidelity and diversity. For detail, compared with SSD, SAMCT generates the overall contour such as road and building more clearly, where SSD often fail to generate the straight line. Furthermore, SAMCT show good performance on generating a finer structure, such as the tree trunk and leaves, as well as the traffic light and poles. And also, SAMCT can generate the uniform shape of vehicle compared with the SSD. So we extend our model to conditional generation. In the same context as the in-painting, out-painting, and image-to-image generation in image diffusion model, we also show this application in our task. Here is the comprehensive scenario about our applications. First, we extend our model to refine the predictions of semantic scene completions models. Here, semantic scene completion tasks aim to jointly estimate the complete 3D geometry and semantics of the scene from the sensors like camera or LiDAR. However, between the semantic scene completion estimate scene and ground truth have a huge semantic and geometric gap. This gap can degrade the performance of the downstream tasks such as the path planning and map construction things. So our models aim to change these results to more refined things like image-to-image generations concept. So we can refine the semantic scene completion results by simply concatenating the triplane of the existing XST results and the corrupted triplane. So these figures are the result. After our refinements, it shows alignments more closely with the ground truth. Especially monoscene and oak depth results sometimes miss the overall contour, but with our model, you can see that refine the model and refine the road and buildings. And in the SSA, SSC, and SSPNet, our model can refine the fine detail things. So this table shows our refinement process provide the important to all SOTA SSC models, both IOU and MIOU. The IOU is used to evaluate the scene completions, while the min IOU provides the measures for the quality of the semantic segmentations of the completed scene. An additional application is outpainting and inpainting by manipulating triplane feature during our diffusion process. So our scene is outpainted to the city level without any additional training, and also by manipulating triplane feature, our model seamlessly integrates the object into the scene via inpainting. So let me explain outpainting and inpainting more detail. To outpaint scene seamlessly, we extend the triplane instead of the 3D scene without any additional training. So our model generates the novel triplane that is partially overlapped with the original triplane. So we define a binary spatial trimask covering the regions to be outpainted on triplane for 3D aware outpainting. So this is the result. Our original scene's resolution is the 2056, 2056, and 32, and it outpainted to the city level like this. So while our model is trained using only fixed size of the triplane, which is only contain the street scene, the results demonstrate that our model can city level scene without the additional training. And these figures provide the close-up view of the city scale scene. And also in the inpainting, we use a tri-mask covering the inpainting region on triplane. By doing so, inpainting randomly added a 3D scene, seamlessly adding, removing, or modifying object while maintaining the consistency of the scene. And it allowed us to control the generation process on the masked region. So this is our inpainting results. The red box refers to the inpainting regions. So for detail, removing and adding objects show our model seamlessly remove or insert an object in the scene. And modifying object means change the object to the another things. And on the other hand, the modifying scene show our model altered existing scene components. So I would like to summarize my presentation. So in this work, we enhance the outdoor scene generation through the triplanar representations, leads to not only computational efficiency but also visually appealing with enhanced semantic details. And we extend our model to several applications, including inpainting, outpainting, and semantic scene completion refinement. Especially by manipulating triplane feature during the diffusion process, we achieve the seamless inpainting at both the object and scene levels, and through outpainting, we extend the scene from the fixed side to the city level scale. And finally, our model is used to more close align predict scene of existing semantic scene completion models with the actual data distribution using our learned 3D prior. And here is our open source. If you'd like to study the code for our model, please visit our GitHub. Yes, that's it. Thank you for the listening.